And for our second installment of L'Hôpital's, we're going to do some example problems. Nothing too crazy. Our next one will get more into get a little nutty, more algebraic. So these, let's just jump right into it. I've got written them both up here. I got 0 over 0 case and our infinity over infinity cases. We're going to talk one more time about this. That if you get 0 over 0, and infinity over infinity, and negative infinity over positive infinity over negative infinity, or shit, maybe you have negative infinity over a negative infinity, while plugging in to your original function, your limit values, you get one of those indeterminate forms. We say that we can now take a derivative on the top and a derivative on the bottom and say that it is the same thing as what we just started with, provided the limit exists, of course. Let's go. Got a few problems here. Oops, move it down a little bit. There we go. We're going to evaluate these following limits. So let's just do this first. Now you might be looking at this first problem going like, I can solve that thing without L'Hôpital's. Right? We had that conjugate trick. Good. Just hit it top and bottom. Everything's going to pop out super nice. But let's try and use a different method. Most of the time you're pretty much forced into using L'Hôpital's, but other times you're not. So we have the square root of 3 plus x minus the square root of 3 all over x. So the game is we want to pretend like we're going to just plug in x equals 0. We're going to pretend like we're just going to take this and we're just going to plug it in here and here. So what would be left if you were to just cover those things up? What's going to happen here? So if I was to write this thing in, I think you get the square root of 3 minus nothing minus the square root of 3 all over nothing. Not the square root of 3 minus the square root. Isn't that just 0 over 0? Then we get the 0 over 0 case. That means L'Hôpital's. Let's go. That means we're going to use L'Hôpital's at this point. So when we do this, this is going to be how we're going to write it in. We're going to write this stuff in. Oops. We can get rid of something. Oh, never mind. Don't do anything. Don't mess with it. So when we do this, we're going to say we're using L'Hôpital's. We're going to take a derivative of the top and the bottom. We alert the reader by when we use our equal sign, just write LH rule circle around it. It just lets the reader know, hey, I'm about to do this, so they can follow along with what the heck you're doing. And we rewrite it. The limit is x still tends towards 0. But now we're going to take a derivative of what's up top. All right, we're going to take this derivative. What's the square root of 3 plus x's derivative minus the square root of 3? Right, minus the square root of 3. That shit's going away. So the square root of 3 plus x's derivative is 1 over 2 times that value. I'll let you double check to see, make sure that's correct. But that's the derivative of the square root of 3 plus x. And now let's take a derivative on the denominator, on the bottom right here. We're going to pop that in right here. So the derivative of x is equal to 1. Cool, I no longer think we have a 0 over 0 case. Actually, I think that's impossible once we clean it up. There's only one variable there. That 1 doesn't mean anything. Hey, there it is. We're done. There's not a variable up top, so there's no way in hell we could ever play this game again. So we can just now evaluate the limit. 1 over 2 times the square root of 3 plus, and now we're going to take this thing here, This, we're just popping in, plus that 0. Sometimes it's a value, maybe it's 7. You can get some, I don't know, so it's 1 over 2 times the square root of 3. And there is our solution for our first one. L'Hôpital's in action. Let's keep rolling. Here's our next, and man, I'm guessing this is probably going to be, this will be in your homework somewhere. This is a classic. So we're going to talk about the limit as x tends towards infinity here. And we're going to think about where the end behavior, where does shit go? Because you can't plug infinity in, but we're going to pretend. We're going to use quotes and shit as we do this. So as the natural log x, I'm just going to draw it in real quick and we'll get rid of it. Natural log of x. I think I've shown you this. It looks like this, right? Y equals the natural log of x. Cool. Cool. So it's looking like this. And you see how it's concave down? So it's starting to flatten out. But it continually will be positive. It's going to continue to increase, just slower and slower and slower. Because the derivative, isn't that y prime? Isn't that just 1 over x? So if you plug in any values of x that are positive, the derivative is going to be positive, which means it's increasing. Granted, as the x values get bigger, the derivative gets smaller, but it's still increasing forever. And infinity is a big freaking number. Oops, it's not a number, it's a concept. It's saying if shit gets really big in your freaking inputs, the outputs also get really effing big. That's the game. It doesn't look like it. This used to screw me up. I was like, there's no way the y values go to infinity. But they do. Infinity, don't try and think about that too hard, but they do. So here's the moral of the story. You plug in infinity, plug in, I'm using quotes, you plug that shit in, you get infinity. Now if you plug infinity into x, again, using quotes, you can't plug infinity into anything, you get infinity. So we got an infinity over an infinity case. There we be, L'Hopital's. We can use it. So let's alert the reader we're about to use L'Hopital's rule. We rewrite the limit as x tends towards the whatever that value is. Well, this time we're not using a number. We're using a concept that we're tending towards. So it's not actually a value of a. So we take the derivative of ln of x, and that's, oh shit, that's 1 over x. Now we take the derivative of x, and the derivative of x is equal to 1. I think we're ready to roll. So we got the limit as x tends towards infinity of 1 over x, and you know that equals 0. If you don't know that equals 0, shame on you. Shame on you. That was the whole concept of 2.6. The whole concept of limits and how we solved everything. Now, if you just brain farted and didn't know that, and you're like, oh yeah, I remember now, that's fine. But not knowing this fundamentally, I'm very scared for you if you're trying to go to Calculus 2. Even if you pass the class, I think you're going to be very sad about that. If things like this is still like, I don't get it, oh, that's going to be rough. So there it is. We got that it goes to 0. Moving on. Enough of my lecturing. Now this. There's no algebra you're going to be able to do this to try and solve it, I don't think. Just like the problem back here. What sort of fancy algebra are you going to do to this? Huh? You going to do some fancy algebra to that and make it pop out without using L'Hopital's? I doubt it. You wouldn't want to, though. L'Hopital's is pretty simple for this. So now as we go over, I don't know if there's some, maybe there's some cool algebra we could do. Maybe. I don't know. Well, letting you know, if we were to just plug this thing in, well, we get the square root of 1 minus 0 over 2. That's 0, and then the bottom would be 0 squared. All right, cool. We got the whole point. We got 0 over 0. Just wanted to double check, and you should too. Don't just assume. Because I'm an asshole like that would be happy to give you problems that aren't 0 over 0 or infinity over infinity. Just watch you chase your tail. I'd have a good time. So make sure to plug those numbers in first. Make sure that you know the case you're dealing with. All right, cool. So now that we have it, we can now use L'Hopital's rule again. So we're going to rewrite our limit. The limit is x tends towards our a value. Well, that's just 0 in this case. Now this time let's mix it up. Let's take the derivative on the bottom first, just so we make sure that we're seeing this a little bit better. So we take a derivative at the bottom, and that's 2x. Remember, no, we're not doing quotients. There could be a quotient in one of these frickin' problems, but don't do frickin' quotient rule. If you're ever doing quotient rule with L'Hopital's, really question yourself. Don't do frickin' quotient rule. Don't do quotient rule. All right, so now let's go through and let's take a derivative at the top. Let's start piece by piece. Let's start with this. The derivative of the square root of 1 plus x, and that's 1 over 2 times the square root of 1 plus x. Again, go look it up if you don't know why that's not the derivative. By this point, you should know how to take derivatives. The derivative of -1 is, well, we know that's 0. And then we take the derivative on our minus x plus 2, so we're going to get our minus 1 half. All right, well, let's clean it up a little bit. Let's see what we got. The limit is x tends towards 0. 2x, we got 1 over 2, 1 plus x. All right, there it is. Cool. Well, let's just go evaluate this thing. So we go to plug it in, and we're like 1 over 2 times 1 plus nothing minus 1 half all over 2 times 0. So we plug that thing in, and we got, oh, that's 1 half minus 1 half all over 0. So we got 0 over, wait a second. We get 0 over 0 again. But this happens. When you do L'Hopital's rule, it's not equal to that. We weren't allowed to plug it in, because we had another 0 over 0 case. Dang. But we wouldn't know unless we tried. So I use these equal signs, but now that I'm done going, oh shit, nope, that's not true. No, we can't just plug it in. That's just this little, what we write in green. just saying it's one of those cases. It's not actually equal to that shit. This is just a 0 over 0 case. What you saying? Just do it again. Just do L'Hopital's rule one more time, okay? So I'm gonna save you some of the work on this one, right? Just limit it. Here, L'Hopital's letting you know what's up, and this is gonna end up becoming what's this? The limit as x tends towards 0, and we're gonna get what is it? Negative 1 over 4 times 1 plus x to the negative 3 halves power all over 2, right? So took the derivative of the top, the 1/2 clearly went away, but this derivative of 1 over 2 times the root 1 plus x is equal to this down here, that derivative. They match up, okay? I just jumped the steps because we should be past taking derivatives at this point. And now we are allowed to plug it in. There's no way that we're going to have any issue. We know there's no issue because there's no more variable in the denominator. Oops, one too many. So now we can go and just plug it in with our zeros. So it looks like we're going to get negative 1/4. This one you plug in 0, you're just going to get 1 all over 2, and this is equal to negative 1/8. And there's our solution. So this one we had to do twice. And it might look crazy, but I mean, seriously, you can jump aside and take this thing. Your 1/2 times 1 plus x to the negative 1/2 power and take a derivative and get to here. I'm certain you can do that, right? So there's the trick, there's the tough. We're going to come back with some actual like challenging ones that are still straightforward, not getting into the weird forms. So next one will be some more challenging of this form with 0 over 0, infinities over infinities, and then we'll get into the other indeterminate forms.